Another flashback I talked about earlier, but I want to talk about again. You can find the system enthalpy for a reaction if you have a table of enthalpy values. And you take the sum, which is what that symbol is right there. You take the sum of all the enthalpies of the products, and you subtract from it the sum, which is that symbol right there too, of all the enthalpies that are reactants. And if this is totally like blah, 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 and you can't get your mind around it, well, let's do an example. It's not a hard process. You do need a table of enthalpy values to make this happen, but here's how this works. So let's say we want to find the enthalpy of this reaction, which is 2 hydrogens and an oxygen making 2 waters. Okay, we're going to need the enthalpy values for liquid water. We're going to need the enthalpy values for both hydrogen and oxygen. And if you remember from this stuff back in Chem 221, Chapter 5, and if you don't, I do recommend you look in Chem 221, Chapter 5, just to make sure you're up to speed with it. Some of those species have enthalpies of 0. And all of the elements in their standard states have enthalpy values of 0. So the overall way to find the delta H, products minus reactants. This part right here, that's the products. We have 2 liquid waters. And then there's a minus, and then the part in square brackets here, that's the enthalpy of the reactants. So products minus reactants. Now, the number that's right there, that's the value when you look it up for water as a liquid, okay? If you look up hydrogen and oxygen, they have values of 0. And notice that because of the stoichiometry, we're going to multiply the water by 2. If hydrogen had a value, we'd multiply it by 2. Oxygen, though, we just multiply by 1 because that's the stoichiometry of it. If you look this all up in your book and you do the problem right, and I encourage you to do it, you should get a delta H for this reaction minus 571.70 kilojoules per mole. And just as some quick reminders, all right, the pure elements have values of delta H equal to 0. These are heats of formation, all right? We look the values of delta H up in the table, and there's one in problem set 5 to use. This is an exothermic reaction because delta H is a negative number. If it was a positive number, we'd call it endothermic. And again, that little 0 there just means standard conditions, 298 Kelvin, 1 atmosphere of pressure, etc., etc. So that's kind of a quick flashback to Chem 221. We're going to do something very similar here. In this case, it was delta H equals delta H products minus delta H reactants. We're going to do similar things with other thermodynamic quantities here in just a little bit. For example, you can calculate the change in entropy for a reaction just like you did the change of entropy and change of enthalpy for a reaction. And you can see the problem here. It looks very similar to what we just did. If you want to find the delta H of a reaction, say this reaction we looked at earlier, it's all the delta S's of the products minus all of the delta S's or the S values for the reactants. So just like before, we need to look up the values, products minus reactants. We'll have 2 liquid water values minus the 2 hydrogens and the oxygen. Now, in entropy, remember the only time you have 0 entropy is for the pure crystal at 0 Kelvin, which is like never. So what that means is that unlike enthalpy, we do need to look up values for liquid water, for hydrogen gas, and for oxygen gas. So if you do this, all right, the overall delta S, it's products, which is that part right there, minus this part right here, which is the reactants. So products minus reactants, and the stoichiometries follow. So we're going to multiply the liquid water by 2. We're going to multiply the other ones by whatever they need to. And unlike enthalpy, H2 and O2 have entropy values. You need to look them up, okay? So when you do this, 2 moles of product minus the 2 hydrogens plus 1 mole of oxygen, oxygen, you get a delta S of the system, which we'll talk about in a little bit here, negative 326.9 joules per Kelvin. All right. So what this says is there's a decrease in entropy for this reaction. And if you think about why that's the case, you can see why too. We have 3 moles of gas going to 2 moles of liquid. So first of all, entropy is always higher for gases than it is liquids. So turning gases into liquids, entropy doesn't like it. All right. Also, we have 3 moles going to 2 moles, and 3 moles of reactant is more disorder than the 2 moles of product. So the matter is becoming more concentrated. Entropy really doesn't like this reaction because you have gases going to liquids and 3 moles going to 2 moles. Nothing about this is making entropy very happy. Let's calculate the standard entropy change for this reaction. This is copper metal reacting with half of an oxygen gas to make copper 2 oxide, CuO. And again, the process we want to use, entropy of products minus entropy of reactants. So you can see the different values right there. All of them are positive numbers initially because the only time you'll have 0 is those pure crystals at 0 Kelvin, which is never, and also individual entropy values will never be negative. So anyway, we take the copper oxide, which is this number, and subtract just the copper and 1/2 the oxygen. So do this in your calculator or just see what happens here in a little bit. The entropy here, copper oxide minus the copper and half an oxygen, you end up with a negative 93.12 joules per Kelvin value. So entropy is decreasing in this reaction. And again, because a gas is being formed into a solid, and because you have 1.5 moles going to 1 mole, all of those things make entropy not like this reaction and give it a negative number. If entropy gets a positive number, an overall positive delta S, then entropy is happy, an increase in entropy, etc., etc. Another thing that we need to talk about here real fast before we get into the gist of this chapter is calculating an entropy of formation. And that little f right there is something that's really important for scientists. The table of thermodynamic values, which is at the end of problem set 5, is basically a list of formation values for enthalpy and for entropy. And in Chem 221, we talked about the enthalpy of formation, and that's when it gets a little f right there. And it can be a formation enthalpy if, and only if, you have 1 and 1 only mole of product. And the other thing is that you have to have reactants as elements in their standard states. So you can only have an entropy of formation, or an enthalpy of formation for that matter, if 1 mole of product and reactants are elements in their standard states. So this reaction right here, where hydrogen and oxygen are making liquid water, that is a formation reaction. And if we want to define the entropy of formation from it, this would be a good candidate because we have 1 mole of product, 1 mole of liquid water, and all of our reactants are elements in their standard states. So we can calculate those values. We'll look up in the same tables that we did before. We'll take the products, which is 69.9, the water value, and we'll subtract the reactants, which is 1 hydrogen and half of an oxygen, and we end up with an entropy of formation, negative 163.5 joules per Kelvin. So this is how you find the entropy of formation. You can also do the similar kind of thing to find an enthalpy of formation, but the difference with enthalpy of formation is that all of the reactants had values of 0. In enthalpy, H2 and O2 gas would both have values of 0, but with entropy, you actually have to calculate what those numbers are. So if you have the entropy of formation values, that's awesome, but if you don't, you can calculate them using this system right here. Which of the following is the reaction for an entropy of formation? Now remember that to have an entropy of formation, or any formation for that matter, you can have 1 mole and 1 mole only of products, and all of the reactants must be elements in their standard states. So if you look at the first one there, making manganese 2 hydroxide, well, we do have 1 mole of product. That's cool. However, hydroxide nor manganese 2 plus are reactants as elements in their standard states. It's not manganese metal and oxygen gas and hydrogen gas, which would be the elemental versions. So A is not a formation reaction. B, you can see there's lots of products, and you can only have 1 mole of product in a formation reaction. B would be a formation if it was reversed. If you had KClO3 as the product, and all of those pieces there were the reactants, but it's not, so that's the way it goes. Now, C has 1 mole of product, all right, which is cool, but it doesn't have, again, elements as standard states for reactants. CaO and CO2 are both compounds. Those aren't elements in their standard states, so that one doesn't fly either. But answer D, if you look at that, we have 1 mole NaOH, we have 1 Na, elemental sodium, we need 1/2 of oxygen and 1/2 of hydrogen, and those are elemental states. Well, guess what? Answer D is a formation reaction. And I bring this one up because I hate using fractions when it comes to balancing reactions. But in a formation, whether it's enthalpy in Chem 221 or entropy now, you sometimes have to use fractions. And I don't necessarily like it, but even I, with my PhD, I have to use fractions when it comes to formation reactions. Answer E is not a formation either, because you have 8 moles of product. You can only have 1 mole of product, etc., etc. We talked about the first law of thermodynamics. First law says energy can't be created or destroyed. We talked about the third law of thermodynamics, where the only time you're going to have 0 entropy is for that perfect crystal of an element at 0 Kelvin, which is basically never. The only one left to talk about then is the second law of thermodynamics, and this one is huge. It may not look that way at first, but trust me, this one's going to rock our world. Second law states that a reaction is only spontaneous, i.e. product favored, if the delta S for the universe is positive. Now, if you're talking about delta S of the universe, you have to realize the universe has a system and a surroundings, all right? The chemical system, in our case, we're looking at, and everything else around it. If you're going to have a spontaneous product-favored reaction, you must have an increase to the entropy of the universe, to the disorder of the universe. That's when you're going to have spontaneous product-favored, usually irreversible processes. So if we want to calculate the entropy of the universe, we have to first of all calculate the entropy of the system. And the entropy of the system is usually what we do when we calculate matter dispersal. And that's like classic entropy, all right? Because classic entropy talks about moles being dispersed and liquids versus gases, et cetera, et cetera. But we also then need to think about the entropy that's created through energy dispersal. And that's going to be the delta S of the surroundings. So if we can calculate the delta S of the system and the delta S of the surroundings, we can add them together. And if the delta S of the universe is greater than 0, that means its reaction's going to occur. It's going to be product favored. And on the other hand, if delta S is less than 0, then the reaction won't be product favored. It'll be reactant favored, not as likely to occur. If you're kind of underwhelmed by my description so far as to why this is important, trust me, I understand. But here's the thing. Let's say that someone said, hey, how would you like the magic power to predict if a reaction was going to occur? I mean, any reaction, any chemicals, blah, blah, blah. Well, you'd probably say, score. Absolutely, I want that. Superpower. But anyway, all right, superpower maybe is an exaggeration, but hopefully you get the idea. This law is actually the equivalent in a chemistry term for that kind of superpower. Because if you can calculate the delta S of the universe, and if you find it's greater than 0, that reaction is going to occur. And it can be any combination of chemicals, any conditions, blah, blah, blah. So this is why scientists want to do it. They want to know if sodium chloride reacts with silver nitrate, all right? Or if potassium hydroxide reacts with hydrochloric acid. Those are the kind of questions that scientists would love to be able to tell, and this is their key to finding that out.
When we dissolve ammonium nitrate in water, The dissolution is an endothermic process. The temperature of the solution decreases over the course of the reaction. The reaction, though not favored energetically, is favored by entropy. It is said to be entropy-driven. As the ammonium nitrate dissolves, the entropy of the system increases. At the same time, the surroundings lose energy and experience a decrease in entropy. The increase in system entropy, however, is greater than the decrease in the surroundings entropy. Thus, the total entropy, the sum of the entropy changes in the system and surroundings, increases as demanded by the second law of thermodynamics.
We're going to go back to the example of ammonium nitrate dissolving in water. Woohoo! Not very exciting, but remember, it is kind of exciting scientifically because it's an endothermic process. The temperature is going down. On the other hand, it is spontaneous, all right? The reaction is occurring. So, using the second law of thermodynamics, delta S of the universe equals delta S system plus delta S surroundings. Well, overall, delta S of the universe must be greater than 0, okay? So the question is then, what's happening here? Delta S system, delta S of the surroundings. Well, the surroundings is related to the temperature. It's pulling energy from the outside in, all right? So if energy is being pulled from the outside to the inside, entropy of the surroundings is not a positive number. On the other hand, ammonium nitrate, that nice ionic lattice solid being dissolved into liquid water, breaking up into ammoniums and nitrates and stuff like that, that must have a delta S system value that's greater than 0 because something is making delta S in the universe greater than 0. So if the matter distribution is overpowering the endothermic value of the delta S of the surroundings, that's what's going to make this reaction occur. It's going to make it spontaneous. Let's go back and look at this reaction real fast. We're going to calculate the delta S of the universe for hydrogen and oxygen making liquid water. And earlier in examples, we did both the entropy calculation, which is delta S of the system, by the way, and we also did the delta H calculation, which is going to be related to delta S of the surroundings. If you go back in your notes, the delta S of the system, which was the products minus reactants thing we did earlier, came out to be negative 326.9 joules per Kelvin, all right? And we talked about how that's entropy disfavored, i.e. negative number, because 3 moles of gas are going to 2 moles of liquid, etc., etc. Delta S of the surroundings from other classes you will find is equal to the Q of the surroundings divided by the temperature at which it occurs. And the Q of the surroundings is equal to the negative of the delta H of the system. So what that means for us here is that delta S of the surroundings equals negative delta H of the system divided by the temperature. Now, the delta H of the system is actually a number we already calculated. That was the delta H of products minus delta H of reactants. And we saw that the hydrogen and the oxygen had 0 values, but water was a number we could look up. We ended up calculating it was a negative 571.70. So we're going to take this delta H of the system and we're going to calculate the delta S of the surroundings. And we've already got delta S of the system, so you can probably see where this is going. First of all, let's do the delta S of the surroundings. So negative of the delta H is negative, negative becomes a positive. We'll turn the kilojoules part of delta H into joules. We'll divide it by the temperature at which it occurs, and these are all standard conditions, so 298. Delta S of the surroundings, positive 1917.5. We've got a 1917.5 delta S of the surroundings. We have a negative 326.9 delta S of the system. So we've got all the pieces now that we need to calculate the delta S of the universe for this reaction. And again, on that last slide, delta S of the system, negative 326.9 joules per Kelvin. Delta S of the surroundings, positive 1917.5 joules per Kelvin. Make sure that you translate, by the way, delta H, which is usually in kilojoules, to a joules per Kelvin if you're doing this process. But anyway, second law of thermodynamics says that delta S of the universe equals delta delta S of the system plus delta S of the surroundings. So if you add those two pieces together, positive 1590.6 joules per Kelvin. And this is a positive delta S of the universe value. So that means this reaction is product favored. And to be honest, thank the stars it is, because this is the formation of liquid water. And liquid water, which is very abundant on the Earth, thankfully, forms pretty readily. Now, the delta S of the system number right there implies that maybe it wouldn't, because the delta S of the system, 3 moles of gas going to 2 moles of liquid, entropy here is not very happy. But fortunately, the delta S of the surroundings is so positive, it overwhelms the delta S of the system, giving an overall positive delta S value. So we hope that water forms. It does. It has a positive delta S. Woohoo, you just used a superpower. You found out that this reaction is spontaneous. It's going to happen. It's product favored. So that's good. Water forming from the elements does occur. And that's what's kind of cool about all this.
A balloon filled with hydrogen and surrounded by air represents a potential chemical reaction. To initiate the reaction, we need to ignite the balloon. The hydrogen will combine with oxygen in the air to form water in gaseous form, releasing considerable energy in the process. At the molecular scale, the molecules of gaseous hydrogen, H2, and oxygen, O2, combine to produce H2O, water, generating heat and light. In the combustion of hydrogen and oxygen, the entropy of the atoms in the sample, or system, decreases. This decrease occurs in concert with the transfer of thermal energy to the surroundings, leading to an increase in the entropy of the surroundings. The entropy increase for the surroundings is greater than the decrease for the sample, so the net change in entropy is upward.
So it's kind of interesting, like the hydrogen and oxygen by itself, the entropy of the system was totally fine with it, like don't change, all right? On the other hand, once the hydrogen and oxygen were allowed to react to make water, lots of energy was released. So even though you end up with fewer moles, and fewer moles of liquid, by the way, which is all entropy disfavored, the overall energy is distributed really well through the outside. So the container would feel warm, or other molecules would rotate, vibrate, move around faster, that kind of stuff. This is how you can think about these reactions. And if you compare again the system entropy to the surroundings entropy, you can actually figure out if a reaction is going to be product favored or not. So this reaction with a positive delta S would be very product favored. We expect water to form. Which of these reactions would you expect to have the largest positive entropy change? Okay, really good question. Now, the first one is 2 molecules of gas going to 2 molecules of gas, all right? Probably not going to be a big entropy change there. You could argue that maybe you're getting more ordered because you're going to individual I2 and F2 instead of the mixture right there. But we would not expect to necessarily have a very big positive energy change. It might even be negative. Honestly, I don't know. But I'm not excited by it, as you can probably tell. All right. Now, B, gas going to liquid, we would absolutely disqualify that because gases have more entropy than liquids. Gases going to liquids would not have a positive entropy change. Let's skip to D real fast. A liquid going to solid would be equivalent because, again, solids have less entropy than liquids, so that would probably not be favored. But let's look at C now. Now, C is an example of a combustion reaction, which is something we talked about in Chem 221, where you take something organic. This is benzene, C6H6, by the way. It reacts with oxygen. It's got a fraction there. I know. I'm going to get over it. Anyway, it makes CO2 and some water. Okay. Now, this one, I think, is going to have a big entropy change for 2 reasons, all right? The first reason is that if you look at the moles of gas, all right, 15 over half, 16 over half would be 8. So you have like 7.5 moles of oxygen plus 1 mole of liquid. That would be 8.5 moles on the reactant side. And those 8.5 moles are going to 9 moles total. So fewer moles going to lots of moles. That's making the entropy of the system actually happy, more disorder. Also notice that one of the moles on the reactant side is a liquid. Everything on the product side is a gas. So if you can go liquid to gas, that's a pretty good indication that's going to be entropy favored. But the other thing is that because it's a combustion reaction, those reactions are super exothermic. They burn easy. So that reaction is going to have a good delta S of the surroundings as well. Because if you burn something, energy is released. It goes into the outside. So for both system and surrounding values, I would argue that C is the best answer. 8.5 moles going to 9 moles is definitely good. A mole of liquid turning into gas, also good. Combustion reactions make the delta S surroundings going to increase as well. Very cool. Also notice there what I did for delta S of the surroundings. I used an enthalpy term, an exothermic reaction, which is what a combustion reaction is, to justify why delta S of the surroundings would be positive. That's where that delta S of the surroundings equals negative delta H over T part comes in. But you can also see how we're going to come back to enthalpy here in a little bit. Enthalpy is a little easier to use usually in chemistry than the delta S of the surroundings. So here are several combinations that talk about if you have a spontaneous process or not in terms of delta S of the universe, all right? Now, delta H is proportional to negative delta S, or negative delta H is proportional to S of the surroundings, all right? And you can see there's 4 possibilities, and they all involve essentially enthalpy versus entropy. Now, what's confusing about using the delta S of the universe is that you have to convert delta H to the opposite for delta S of the surroundings, but it can be done. I also want you to see that there are 4 possibilities. In one way, the enthalpy and the entropy are working together to make the reaction spontaneous all the time, which would be delta S of the universe greater than 0. You also have a condition of delta H and delta S, which are working together, but to prevent a reaction from going. And there are some reactions which won't be spontaneous like ever. And then there's 2 conditions in the middle where either entropy or enthalpy want the reaction to go, but the other one doesn't. And there will be a temperature dependence on that. We're going to talk more about this, but in a different context here coming up. But these 4 possibilities to explain if a reaction is going to occur or not can be really helpful. And we'll look at this in a little bit different light in just a little bit.